Welcome to today's Explainer, where we're going to dive straight into the fascinating world of vector semantics and discover how AI actually reads human language. If you've ever wondered how a machine can seemingly understand the complex nuances of our words, you are in the exact right place. We're going to break down the exact mechanisms that make modern language models possible.
Here is our roadmap for today. We'll cover the distributional hypothesis, turning words into math, the word-to-vec breakthrough, the magic of analogies, and finally, the dangers of bias.
To kick things off, let's look at this brilliant philosophical insight from the ancient Chinese philosopher Zhuangzi. Written centuries ago, he understood that words are basically just the nets we use to catch meaning. Just like a net is a tool to catch a fish, the word itself isn't the final goal. The underlying meaning is. And it's pretty wild, but this ancient philosophy perfectly captures how modern computer science approaches language today.
Now, you might be wondering what biology has to do with AI, but it actually mirrors language beautifully. Take the Smilodon, the famous saber-toothed tiger, and the Thylacosmolus. One was the placental mammal, the other a marsupial. Totally different species living in completely different regions of the world. Yet they evolved identical giant saber-toothed canines. Why? Because they lived in similar environments. Well, in linguistics, we see the exact same phenomenon. Words develop their meaning based on the environment they live in.
Section 1. The distributional hypothesis, defining words by the company they keep.
Let's say you read the sentence, "Ong choy is delicious sautéed with garlic." Now, even if you have never heard the Cantonese word ong choy in your entire life, your brain instantly gets to work. You guess it's a food, probably a leafy green like spinach or chard. But how did you know that without reaching for a dictionary? You knew it simply because of the neighboring context words, like delicious, sautéed, and garlic. The environment of the word completely gave away its identity.
And that is absolutely crucial to understand, because algorithms don't read dictionary definitions. Instead, they rely on the distributional hypothesis. Formulated back in the 1950s by linguists, this hypothesis just states that words occurring in similar contexts tend to have similar meanings. AI algorithms use this exact rule to map out which words hang out in the same neighborhoods.
Section 2. Turning words into math, building the co-occurrence matrix.
So how do computer scientists turn these word neighborhoods into raw math so a machine can actually process them? Imagine scanning through a massive text corpus, like literally all of Wikipedia, and just counting how often target words appear near context words. You'd create a giant grid, or a co-occurrence matrix. Take the word cherry. It appears near the word pie 442 times, but almost never near data or computer. Suddenly, the word cherry isn't a string of letters anymore. To a computer, it's represented by a list of numbers, which we call a vector.
But how do we actually compare these massive lists of numbers? To figure out if two words mean the same thing, algorithms use something called cosine similarity. It's a metric from linear algebra that measures the angle between two mathematical vectors in our giant grid. Think about it like this. If two words appear in similar contexts, their vectors will point in roughly the same direction. And that means the angle between them is going to be very, very small.
And this is where it gets really cool, because the math works perfectly. Going back to our matrix, if you calculate the cosine similarity between the vectors for digital and information, the result is 0.996. That is nearly a perfect one. Because they share context words like data and computer, the algorithm mathematically grouped them together as highly similar, without actually knowing what either word means in the human sense.
Section 3. The word-to-vec breakthrough, from massive grids to intelligent vectors.
Now, those massive counting grids were a great start, but they had a huge flaw. They were mostly filled with zeros. Most words simply never appear next to most other words. So, modern large language models completely drop those massive, sparse counting matrices. Instead, they favor what we call dense embeddings. Rather than a cumbersome vector with 50,000 numbers that are mostly zeros, a dense embedding compresses meaning into a short, powerful list of maybe 50 to 1,000 dimensions. These dense vectors are highly efficient, and they are literally the secret sauce powering the AI chatbots we use every single day.
So, how are these dense vectors built? Researchers use an ingenious algorithm called skipgram. It uses self-supervision, acting almost like a high-speed guessing game. First, it picks a target word. Then, it grabs the real context words next to it. And finally, it throws in some random noise words from the dictionary. The algorithm constantly trains a classifier to guess, does this word actually belong in this neighborhood, or is it an imposter? Over millions and millions of rounds, the internal weights of this guessing game solidify to become our dense embeddings. Section 4. The magic of analogies. Relational similarity in mathematical space.
Once these dense vectors are fully trained on enough text, they unlock a capability that frankly looks like an absolute magic trick. Because these words are now exact points in a mathematical space, you can literally do algebra with language. Look at this equation. Using the parallelogram model, if you take the mathematical vector for king, subtract the vector for man, and add the vector for woman, the closest mathematical point in space to your result is the vector for queen. It is mind-blowing. The algorithms are extracting relational concepts like gender, capitals of countries, and comparative adjectives purely from the math.
We can even track these mathematical neighborhoods across time, creating a sort of mathematical record of human culture. By training vectors on historical texts from different decades, we can watch the math shift as society alters the meaning of words. Back in the 1850s, the vector for awful sat near words like majestic. In the 1900s, broadcast was actually a farming term clustered near scatter and seeds. And in the 1950s, gay was closely mapped to cheerful. We are literally watching semantic meaning evolve visually.
Section 5. The dangers of bias, the reflection of our own prejudices.
But mapping meaning directly from human text brings us to a harsh reality. Algorithms learn our context, which means they also perfectly capture our biases. The data objectively shows us that these algorithms amplify historical prejudices. For example, solving analogies in vector spaces has actually output results like computer programmer is to homemaker. This leads to allocational harm, where AI used in hiring might unfairly downweight women's resumes for programming jobs. There's also representational harm. Studies mirroring implicit association tests show that algorithms mathematically associate specific ethnic names with unpleasant words more than European American names. Why? Simply because that statistical bias existed in the vast amount of human-written training data.
As we marvel at how computers have learned to map the meaning of our words, turning abstract human thought into computable geometry, we are left to ponder one ultimate takeaway. What does it mean that our most advanced technology perfectly reflects our oldest biases? And more importantly, how do we handle the very human prejudices baked into this newly discovered mathematical space? Thanks for joining me on this explainer. And as always, keep questioning the data.